Okay, dear students, let's start from where we left. So we defined our curvature, and I told you before the definition of the curvature that our curvature should be such that it is 0 for a straight line, and of course for a circle of smaller radius it has to be bigger. That's our intuitive thing that the curvature must satisfy. That is, the degree of curvedness of a straight line should be 0, and that of a smaller circle should be, of course, bigger than a bigger circle. Now we defined in case the curve had a unit speed reparameterization, then we simply defined our curvature to be the modulus of alpha double dash. So that was our curvature. In case it was some other parameter, then k would be alpha dot cross alpha double dot divided by modulus of course modulus divided by modulus of alpha dot cube. And we also derived it, calculated it for a circular helix. Now it does actually, our definition of curvature is very much consistent with what we wanted to sort of achieve. For example, if I take the equation of a straight line alpha at t, now we want it to be 0. Alpha at t would be, what do you get? It would be some constant vector times t, where t is the parameter, plus some other constant. Now this is the equation of a straight line in vector form, and if you differentiate it twice, right, you would get alpha. Of course, alpha dot is what? It is just a constant a, and if you differentiate it again, alpha double dot would be 0. And if you substitute it, the cross product of a 0 vector with any vector is 0, so this would be 0. And of course, if we take the equation of a straight line, equation of a circle of radius a, so if I take an equation of the circle, let it be in xy plane, so it would be something like a cos t, a sin t, right, and 0 because I am in the xy plane. And you would see that the curvature, and let's evaluate it to make things easier, to make it more understandable. We just see that what we wanted actually does, our definition of curvature does follow intuitively actually. Now if you differentiate it twice, the first derivative would be, of course, you would have minus a sin t, a cos t, 0, and then you have what? And you differentiate it again, so this is alpha dot, this is alpha double dot, so you would have what? A minus a cos t minus a sin t, 0, right? Okay, then you just substitute the values, and if you see that we have already done the work that we required. No, it's not the same curve. We have done it for right circular helix. The curvature is a divided by a square plus b square, isn't it, when the parameter was t? But if we really think, the difference between the curve, the equation of the right circular helix is alpha is equal to a cos t. In the case of right circular helix, a sin t bt. The only difference is basically that we can think that b is 0 here. So if I evaluate, I should actually get curvature to be a divided by square root of a square plus 0 square, which is nothing but a, oh no, it was a divided, not, it was a divided by a square plus 0 b square, which in our case, in the case of circle, if we do the same evaluation, because we just have to take the cross product and the length of the vectors, we should get a divided by a square plus 0 square, which is nothing but 1 by a. So which means that, because this is basically the equation of a circle with radius a, and its curvature is nothing but 1 by a, which means the bigger the radius of the circle, the smaller the curvature. Smaller the radius of the circle, bigger the curvature. Again, it's constant everywhere. It's just the inverse of the radii. Okay, so our definition of curvature does indeed satisfy our intuition that for a straight line it must be 0, and if we have circle it should be inversely related to its radius. Okay, let's continue further. Now, since we are talking about our unit speed curve, then one thing is clear, as we have done in an earlier small theorem, that is if you have a vector of fixed magnitude or a vector of magnitude 1, as is the case with unit speed curve, because it's unit speed, it must be always equal to 1 for values of s. Now if you have a vector of unit speed, then alpha double dash would always be perpendicular to alpha dash. For any vector of constant magnitude, if you differentiate it, then the derivative would be perpendicular to that vector. Now the derivative of alpha dash would be alpha double dash. Okay, now in the case of a space curve, a curve that lives in three-dimensional space, if you have alpha dash in this direction, now you just imagine, then there are infinitely many possibilities in which direction this alpha double dash would lie. Right? In the case of three-dimensional curvature, if you think of a vector in a three-dimensional space, there are infinitely many vectors which are perpendicular to that vector. But inside a plane, if this is alpha dash, then alpha double dash has only two possibilities. It could be like this or like this, because there are only two possible perpendicular vectors to a vector in our two-dimensional space, R2 in a plane. So in this way, this idea gives rise to the definition of what we call signed curvature of a plane curve. So we start with the definition, and then we see how it is related to the curvature of the curve. Okay, so let me write down the definition. Signed curvature. Let alpha be equal to alpha at s, be a unit speed curve in a plane, be a unit speed curve in R2, that's plane, then alpha dash would be the tangent vector, in this case the unit tangent vector, because it's a unit speed curve. Now there are two vectors perpendicular to alpha dash or t. So we make a choice by defining n sub s. N sub s, which we call the sign normal. Now this is one of the two vectors. Now which one is it? The vector that ns is, we make ns to be the vector, be the unit vector that is obtained by rotating t, this unit tangent vector t, by pi by 2 in anti-clockwise direction or the counterclockwise direction. So in our picture, if this is our plane curve and this is the unit tangent vector in this direction, then our ns would be in this direction. Of course, ns, the magnitude of ns is exactly the curvature, isn't it? But in this case, the magnitude, now we define with the help of this the sign curvature. Okay, now alpha double dash is clearly, as I earlier said, perpendicular to t. No, alpha double dash is actually equal to t. And t is perpendicular to ns. That means alpha double dash is actually parallel to n sub s, the vector that we found by rotating t in the counterclockwise direction by pi by 2 radians. So that means if two vectors are parallel, then one must be the scalar multiple of the other. So it means there must exist a number there exists a number ks such that alpha double dash is equal to k sub s n sub s. This number k sub s is called the signed curvature of alpha, the plane curve. So this number that we got here, ks, is the signed curvature of our plane curve alpha at a point s. So obviously we already know that the curvature of a curve, whether it is inside a plane or three-dimensional space, k is basically alpha double dash, the length of the alpha double dash. Now, which in this case is the same as k sub s, n sub s. Now that's how we define k sub s. That means k must be nothing but the magnitude of k sub s into n sub s, but this is a unit vector, so which means that k must be the magnitude of k sub s. So curvature is the modulus of the sine curvature, which means that also that k could be plus ks or minus ks, depending upon whether it is positive or negative. Okay, now there is a simple basically a simple way of thinking of sine curvature. That's going to be our next theorem. A simple theorem. Basically, you should look at your notes. I emphasize it again and again. The study material provided to you has a lot of things, and you should just go through that. So the theorem that we are going to do now is that if alpha at s is a unit speed curve, is a unit speed plane curve, and let phi of s, phi of s be the angle through which a fixed vector must be rotated, a fixed vector, fixed unit vector, okay, fixed unit vector must be rotated anti-clockwise or counterclockwise to bring it into coincidence, to coincide it, to bring it into coincidence with the unit tangent vector, with t, the unit tangent vector of the curve of alpha. Then k sub s is nothing but the change of phi, change of this angle with respect to our parameter s. Okay, you have a situation like this. You have got a unit vector, fixed unit vector a, right? And then we have got, of course, our curve here. So I've got a unit tangent vector here. Let's call it t. The angle between t and a is phi. That's given. And then we can easily figure out then ks would be the change of the derivative of this angle with respect as we change the point, or as we move from one point of the curve to another point. Okay, so this is the situation we have. So to make it look to look at it in a, so what we have now, I've got a vector a which is unit vector. Then I have another unit vector, that's my t, the unit tangent vector, and the angle between this a and t is, by the assumption by our theorem, phi. Okay, now what we do, we just rotate this vector. We just find another vector b which we can find by rotating this a by pi by 2 radians. Let's call this vector b. Okay, so I've got a vector a vector b, and t is at an angle of phi with respect to a. Then we can write t as a combination of course that's very easy to verify. It's a vector into cos of phi plus b vector into sine of phi. That should be my unit tangent vector. Now if I differentiate both sides with respect to phi, then t dash is equal to a and b are of course constant fixed vectors of unit length. So if you differentiate them, you basically have to differentiate right hand side with respect to s, and using the chain rule, this would be, we differentiated with respect to phi, and it would be d by d phi of a cos phi plus b sine phi into d phi by ds. Now that would be minus a sine phi plus b cos phi multiplied by d phi by ds. Right? Now taking dot product of a with both sides, on the both sides you should have t dash dotted with a is equal to, you just, when you dot product a with b, and b are perpendicular vectors, so this thing would be 0, so it will be just minus a dot a sine phi into d phi by ds. But a dot a is nothing but modulus of a square, and since it is a unit vector, so it is just 1. So therefore it is just minus sine phi d phi by ds. Okay. Now, what is the angle? Now, if you think of our unit normal, the sine normal would be a vector that we obtain by rotating t by pi by 2 radians. So it would be like this. So our n sub s is in this direction. So therefore, the angle between a and n sub s should be phi plus pi by 2. Now, the angle between, now that means n sub s dotted with a, as per our as the definition of the dot product should be the length of ns, length of a, into the cos of the angle between the two vectors. Now the vector a has an angle phi with t, and t has an angle pi by 2 with n sub s. So therefore this should be cos of phi plus pi by 2. And cos of phi by 2 is, now this is 1, this is 1, this is just minus sine of phi. Because cos of phi plus pi by 2 is equal to minus sine phi, and this is a unit vector, so therefore they're all 1. So that means ns dot a is minus sine phi. So if I look at this equation, where was it? The earlier equation I had this thing, t dash a is minus sine phi d phi by ds, but t dash is, by our definition, when we defined our sine curvature, this is k sub s n sub s dot a, because t dash, when we substitute k sub s and s, so this is what we have. But minus sine phi is just this, the dot product n sub s dot a, and when you substitute it, you should get k sub s. The sine curvature is just d phi by ds. Just substitute it here. So therefore this is our sine curvature for a plane curve. And now we have what we call sort of a fundamental theorem for plane curves. And given any differentiable function, a smooth function, it is always sine curvature of some plane curve, and vice versa almost. So that's going to be our next theorem, an important theorem. So you just remember that we can write sine curvature as the derivative of the angle which a fixed unit vector makes with the unit tangent vector. So our next theorem is, just look at your notes. I again and again emphasize that because I don't want to write the whole statement and it's a long one. Though basically it says if k from any interval a b to r is any smooth function, that means differentiable in our case, then there exists a unit speed plane curve with sine curvature same as that of k. Given any smooth function, there exists a plane curve, a unit speed plane curve, which has the same sine curvature as that function. Furthermore, it is unique up to a rigid motion. That means if you have any other curve alpha, let me call it alpha, from interval, let me call it okay, first I mean to say alpha is the curve in which has the sine curvature k. Now if you have another curve alpha tilde which has the same sine curvature, you've got another curve, of course it would be from some interval, let's call it alpha tilde beta tilde 2r2, whose sine curvature is same as k, then the difference between alpha and alpha tilde would be just their orientation in the plane. If one curve is like this, the another would be like this. Oh, I haven't drawn it properly. By that I mean you can, by means of translation and rotation, coincide this curve with the original curve. That means for every smooth function determines a curve, a unit speed plane curve, whose sine curvature is that function, that smooth function, and it is unique up to a rigid motion. And if there is another curve exists which has the same sine curvature, then it should be just obtainable from a rigid motion, from some translation and rotation of the first curve, now which has the sine curvature k. Okay, now let's get on to prove this theorem. Now remember what we have. We have got a curvature a k, a function that is differentiable on an interval, right? And we have to get a curve, let me call it alpha, from some interval. Let's now call it interval alpha beta to r2. We have to get a plane curve so that the sine curvature of this alpha is automatically the given smooth function k, and then the other part is the uniqueness. Okay, now what we do, now this is given. Now what we do is, now we fix some s naught belonging to this interval, and for any other s, belonging to this interval which I already have, I define phi of s to be the integral s naught to s k sub u du. Now I already have this function k. I integrate it from s naught to s, and by the help of this I define this function phi of s, and with the help of phi s I define a plane curve like this. I define alpha at s, my plane curve, to be the integral s naught to s cos of phi t dt. Now with the help of this function, with the help of k I define this phi, with the help of this phi I define the curve. This is sine of phi of t dt, or a pair of numbers, which means it lies in R2, right? The first thing is that you have to remember that this k is different. This k is of course smooth, differentiable, therefore continuous. Therefore, I can just differentiate it. So this is a differentiable function. Then cos is a differentiable function. Then this is the improper integral by fundamental theorem of calculus. This is differentiable. So alpha is differentiable. So if I have to evaluate the tangent vector, so I have to differentiate alpha, because to get the sine curvature I have to show that its sine curvature must be the same as k. Now that's pretty easy to prove, right? So by fundamental theorem of calculus I just differentiated components. So I should have alpha dash at t, alpha dash at s, because my parameter is unit speed. Saying alpha dash at s should be, just differentiate them. So it would be cos of phi of s, that's just the fundamental theorem of calculus, sine of phi of s. So that's my unit tangent vector. Now this is a unit tangent vector. If you look at this, so where does this lie? This lies on the circle, right? So if this angle is phi, right, if we look at this vector, if this angle is phi, then the components here should be cos phi, sine phi. this point should be cos phi sine phi. So it's a unit tangent vector which makes an angle of phi with positive x-axis by just how it is, right? So this alpha dash s, which is a unit vector, it's a unit vector making an angle phi of s with the fixed vector any fixed vector along the positive x-axis. You can take the vector I, the unit fixed vector along x-axis. So therefore, if r is a unit speed, so first thing it's a unit vector. Therefore, our curve, because its tangent is a vector of magnitude 1, first thing is that alpha is automatically a unit speed plane curve. And we also know by the previous lemma small theorem that we did that the sine curvature is actually the derivative of the angle with respect to derivative of the angle which the unit tangent vector makes with some fixed unit vector. And we know that phi is the angle which it makes, which our alpha dash, the unit tangent vector, makes with I, right? Therefore, the sine curvature should be, by our previous theorem, k sub s must be equal to d phi by ds, which is nothing but, by our definition, s naught to s. Again, by fundamental theorem of calculus, this should be just k sub s. So sine curvature, so we have found a unit speed curve alpha with the sine curvature same as the given smooth function k. K at s is the same thing as k sub s. For the second part, the uniqueness part, that in case we have another plane curve with the same sine curvature, then it must be the rigid motion of the first curve. It must be obtainable from that by a rigid motion, by some rotation followed by some translation or something, a combination of that. Alright, okay, now let phi tilde s be the angle that the unit tangent vector of this another curve, unit tangent vector of this curve alpha tilde at s makes with positive x-axis. This is another curve, right? Then of course, if I define, let me write it like this, then r tilde dot at s, why should I write dot, because this is a different, this alpha. If that is the case, then then by reversing the steps in the earlier, what I have done in the earlier case, I must have r tilde, let me call it dot s, differentiation with respect to the parameter s, right? Because it's a different parameter, just for distinction, nothing more than that. Let it be cos of this phi s. Using the earlier part, I can just reverse the steps and find this sine phi tilde s. Just reversing the steps of the earlier case, right? Then what you do, you just integrate both sides from s0 to s. Now when you integrate both sides from s0 to s, by fundamental theorem of calculus, it should be r tilde at s minus r tilde at s0 should be equal to the vector s0 to s cos, let me call it phi t dt. Of course, we changed the variable of integration because it was s is here, so it's a dummy in any case. I could have used any other alphabet. So that, it should be here. Then I have s0 to s sine of phi tilde t dt. So this is what I get. Okay. Now, which means that r tilde at s, this new curve must be s naught to s cos of phi tilde t dt, comma sine of s dot to s, integral of sine of phi tilde t dt plus this vector r tilde at s naught. Let's call this equation 1. Now we know by previous theorem that the sine curvature is actually this angle differentiated with respect to s. So this is of course ks, right? So which would give us, if I integrate both sides with respect to, again using the fundamental theorem of calculus, so it would be s naught to s k sub u, k at u du must be equal to phi tilde of s minus phi at s naught. So which would, again taking the sides, so this is some fixed number for some s, so I write it now it as phi tilde of s is equal to integral s naught to s k at u du plus some theta, where theta is the number, phi tilde at s naught is just a constant, a fixed number, phi tilde evaluated at some point s naught. Now if we substitute this phi tilde of s here in equation 1, I just substituted in equation 1, what do I get? Few pages. Okay, so substituting it, I would get r tilde is what I'm writing, alpha tilde. Yeah, you have got alpha. Oh, I have written r here, sorry. So it is all alpha. Oh, it's alpha. Well, you should be able to understand. Okay, let me show it again. This is what we have. I have got this equation. Of course, it is alpha at s naught. This is a fixed vector. Now I made the correction. So it's not r, it's alpha. You look at your notes. I have used actually the alphabet r, but